Okay, let's dive right in. Today, we are cracking a fascinating atomic code. We're talking about characteristic radiation. Now, the best way to think about it is like a secret, unique fingerprint that every single element in the universe possesses. So picture this. Scientists are graphing the energy from X-rays, and they see this smooth, predictable curve. But then, popping right out of that curve are these incredibly sharp, distinct spikes of energy. So what's the deal with those? Where do they come from? And that, right there, is our big question for today. We're basically going to be detectives, figuring out exactly what creates this secret atomic code. So our investigation starts at the source. We're going to dig into what's actually happening to send out this very, very specific message that shows up as these spikes in the spectrum. And it turns out, the answer isn't some crazy complicated external thing. Nope, it's found deep inside the atom, during a moment of some pretty intense atomic drama. So let's break down that drama. Let's look at the sequence of events, this tiny little chain reaction at the atomic level, and the collision that kicks the whole thing off. And here it is, our scene of the crime, the atom itself. You can see the nucleus right in the middle, and it's surrounded by these orbital paths called electron shells. You see them labeled K, L, M, and so on. Just think of them as different energy levels where the electrons hang out. The K shell, that's the one closest to the center, holding on the tightest. Okay, so here's the play-by-play. Step 1, a high-speed electron comes flying in and bam, it collides with an electron in one of those inner shells, usually that K shell. Step 2, it literally knocks that electron right out of its spot, leaving an empty space or what we call a hole. Step 3, now the atom is all out of whack. It's in a really unstable, high-energy state and it wants to get back to normal. So, step 4, to fix everything, an electron from a shell further out dramatically drops down to fill that inner vacancy. Now, these electron jumps, they actually have specific names. If an electron from the L shell drops into a K shell hole, we call that a K-alpha transition. It's the most common one, the most intense one. But what if an electron from even farther out, the M shell, makes that jump to the K shell? Well, that's a K-beta transition. It's got higher energy, but it's a little less likely to happen. And of course, if the original hole was in the L shell, that creates a whole different set of jumps we call the L series. Okay, so we've got this wild atomic drama with electrons jumping all over the place. But how in the world does that connect back to those sharp energy spikes we saw at the very beginning? Let's decode it. Well, when that outer electron falls into the inner shell, it has to release all that extra energy. And here's the absolute key to everything. The amount of energy it releases isn't random at all. It's quantized. That's a fancy way of saying it comes out as a single particle of light, an X-ray photon with a very, very precise and predictable energy value. And this formula, this is basically the Rosetta Stone for decoding the atom's message. The energy of that little photon is exactly the difference between the energy levels of the two shells involved. It's a fixed, predictable calculation, and that right there is the key to the entire code. And this brings us to the big reveal. How does this precise energy code connect to the actual identity of the atom itself? Well, this is where a brilliant physicist named Henry Moseley enters the story. You have to understand, this was an absolute game changer. Before Moseley, everyone organized elements by their atomic weight, but there were some weird inconsistencies. He proved that an element's true identity comes from its proton count, its atomic number. And this completely reorganized our understanding of the periodic table, and it meant that every single element produces its own unique set of energy spikes. And that's the core idea right there. The pattern of those K-alpha and K-beta spikes, it's a unique signature. It's a fingerprint that can definitively tell you what element you're looking at. A tungsten atom will always have a different fingerprint than a molybdenum atom. Always. This chart lays it out perfectly. It shows you the difference from that smooth background curve we saw, which comes from another process called bremsstrahling. See, bremsstrahling radiation is continuous. It's a smooth spectrum. But characteristic radiation gives us that sharp, discrete line spectrum. Its energy is fixed, it's predictable, and it's tied directly to the element. And it's that predictability that makes it so unbelievably useful. So this is all really cool physics, right? But what's the point? Now that we've cracked the code, how do we actually put these atomic fingerprints to use? Well, turns out the applications are all around us, from medicine to materials science. Okay, so take tungsten, for example, atomic number 74. Because of its high atomic number and the fact that it has a super high melting point, its characteristic radiation, its fingerprint, is perfect for general-purpose X-ray machines. That graph you see? That's the unmistakable energy signature of tungsten, and we've built technology specifically around that fact. But what if you need to image soft tissue, like in a mammogram? You need a different tool for the job, so you use a different element. Molybdenum, atomic number 42, produces lower energy X-rays that are absolutely perfect for getting high contrast images of soft tissue. We literally choose the element based on the specific fingerprint we need. And the applications go even further. There's this incredible technique called X-ray fluorescence, or XRF. Scientists can hit a sample with X-rays and then just read which characteristic fingerprints are being sent back. This lets them instantly identify what elements are in anything, from a priceless archaeological artifact to an industrial alloy, all without damaging it one bit. So, if you take one thing away from all this, it's this. Characteristic radiation isn't just some weird physics thing. It's the atomic ID tag. It's what allows us to tell elements apart just by looking at their unique spectral peaks. And that has unlocked some seriously powerful tools in science, medicine, and industry. In the end, we've basically learned how to read an atom's personal fingerprint to identify the very building blocks of our world. It's revolutionized everything from how we see inside our own bodies to how we study ancient history. And it kind of leaves you with this amazing thought, right? If this is an atom's fingerprint, what other secrets about the universe is it just waiting to tell us?